So this is 2019 AP Chem free response number 4. It says a student is doing experiments with gaseous carbon dioxide. Originally, a sample of the gas is in a rigid container at 299 Kelvin and 0.70 atm. The student increases the temperature of the CO2 in the container to 425 Kelvin. And part A says describe the effect of raising the temperature on the motion of the carbon dioxide molecules. So an important distinction here is that it's asking you specifically about the motion, right? Because unless a gas is at 0 Kelvin, it's going to have motion and an average speed and an average kinetic energy. So temperature is a direct measure, or directly proportional rather, to the average kinetic energy of the gaseous molecules. So raising the temperature raises the average kinetic energy. If you look at your formula sheet, kinetic energy equals 1/2 mv squared. Pertaining to motion, raising the temperature raises the average speed of the carbon dioxide molecules. And that should get you for part A. Just say raising temperature raises average kinetic energy, which also raises the average speed of the gaseous carbon dioxide molecules. And part B says calculate the pressure of the CO2 in the container at 425 Kelvin. So this is a simple P1 over T1 equals P2 over T2 problem. P1 over T1 equals P2 over T2. From here you can solve for the pressure. It's asking you to solve for the pressure. Pressure 2 is P1 T1 over T2, which equals the initial pressure is 0.70 atm. And the initial pressure is 299 Kelvin. Then you have to multiply that by the final temperature, which is 425 Kelvin. And getting your calculator out, you should get 0.70 times 425 divided by 299, which will give you 0.99 atm. 0.99 atm. That's part B. And it says, in terms of kinetic molecular theory, briefly explain why the pressure of the CO2 in the container changes as it is heated to 425 Kelvin. So, like stated in part A, raising the temperature increases the average speed of the CO2 molecules, right? So if they're approaching the walls of the container with a greater speed, they're hitting the walls of the container with a greater average force. And pressure is force per area, right? So if you raise the force, then you're changing the pressure. So C, just put raising the temperature raises the average kinetic energy, which raises the average speed of the particle, which causes the particles to impact the sides of the container with more force, changing the pressure. And part D says the student measures the actual pressure of the CO2 in the container at 425 Kelvin and observes that it is less than the pressure predicted by the ideal gas law. Explain this observation. So an important part of the ideal gas law is that it assumes that there are no intermolecular attractions between the gaseous particles, and that the volume of the gaseous particles relative to the container is negligible. If you look at the actual equation that accounts for this, called the van der Waals equation, you'll see a correction factor that accounts for these intermolecular forces and the volume of each particle. But you don't really have to know the van der Waals equation to answer this question. Simply, there's, in reality, intermolecular forces between the carbon dioxide molecules that the ideal gas law does not account for, and this creates attraction between the gas particles, which prompts the gas particles to hit the sides of the container with less force, which creates a pressure that is less than predicted by the ideal gas law. And I'm not going to write all that out, but it should give you a pretty basic understanding of how to answer that type of question. And that's question number 4.